All right, let's go to 8.3. So just like in chapter 7, we had population, sample, then proportion. Same thing here. So now this is a confidence interval for a proportion. So percentages. All right, so let's see what we got here. Final type of estimation we will consider is that of proportions. Simply a percent in decimal form. So example, suppose 80 out of 100 students in a large class pass a test. The percentage of students who pass the test is 80%, while the proportion of students who pass the test is 0.8. Okay, since this proportion involves the entire class, we refer to the 0.80 as the population proportion and write P equals 0.80. Even though we are now working with proportions, we are still doing the same basic task. Point estimate plus or minus margin of error. Okay, so previously we used a sample mean to estimate population mean. In this section, we're going to use sample proportion to estimate population proportion. So the confidence interval will, instead of x bar, it'll now be p hat, plus or minus e. And then e will be z times the standard deviation of p hat. Okay, so now we're going back to z. So we're only using t when we have a sample. We use z for the other ones, for everything else. Okay, remember back to this chart way in the beginning of chapter 8. There it is. Okay, is it a mean or is it a proportion? Proportion, we use z. Okay. Okay. Let's see here. And then as the standard deviation of p hat again, square root pq over n. All right, so as discussed in chapter 7, the prerequisites for the application of the central limit theorem to sampling distributions are NP and NQ being greater than 5. Okay, so NP is greater than 5 and NQ is greater than 5. So we need a big enough sample size. And we check that. Okay. So let's do an example. Each month, the Bureau of Labor Statistics estimates that the national unemployment rate. The unemployment rate is defined as the percentage of the labor force that is not currently employed but could be. Suppose the recent statistics found that 54 out of a random sample of 1,500 Americans were jobless. Okay, we'll go through the whole thing. Determine the point estimate for the proportion. Okay, so first of all, this is a proportion. So remember, we ask how this is being used. Proportion, we're going to use z. So I'm just going to mark on the side. Get used to marking on the side. Am I using z or t? The point estimate is the mean, okay, or the actual proportion here, which is 54 out of 1,500. Okay, so 54 out of 1,500 is 0.036. Okay, that's going to be our P. Okay, now our Q is going to be 1 minus 0.036, which is 0.964. Okay, now if we have a sample size of 1,500, we just want to make sure that PQ is greater than 5, so 0.036 times 1,500. We're good to go. We know that Q is going to be greater 0.964. Okay, so that's just checking the NP and NQ being greater than 5. Okay, so we answered A. Okay, our point estimate is 0.036. We didn't need Q yet, but we're going to need it for the next part. Now we want the margin of error. So the margin of error is z times the standard deviation of p hat. So let's first get our standard deviation of p hat, which is the square root of p q over n. So that will be, for us, 0.036 times 0.964 over 1,500. All right, so square root. I'm going to do parentheses, 0.036 times 0.964, close parentheses, divided by 1,500. So that'll give me 0.0048. Okay, then we want to find our z value that corresponds to a 97% confidence interval. Okay, so remember the chart very back in the beginning of this chapter? We scroll up. There it is, 2.17. Okay, or if we forget that, this 2.17. All right, if we forget that, then second distribution, inverse norm, area, we would have to do 1 minus 0.97, which is 0.03, divided by 2. I think it's 0.15, but I'm just going to put that just to check. 2.17. Okay, so if you forget that, same way you did it with the t. Okay, so 1 minus 0.97 divided by 2, and then inverse norm, that's your area. All right, so E will be 2.17 times 0.0048. So there you're going to get 0.0104. Okay, remember we're dealing with percentages, so it is going to be very small. And then our confidence interval is just going to be p hat plus or minus E. All right, so our p hat was 0.036 plus or minus 0.0104. So let's see, 0.036 minus 0.0104 gives us 0.0256. And then 0.036 plus 0.0104 is going to be 0.0464. Okay, so then here we would say I am 97% confident that the true population proportion of Americans that are unemployed is between 2.56 and 4.64% based on this sample data. So I 97% confident that, and you don't have to write this, the true population proportion of unemployed Americans, is that word? Yeah. Is between 2.56% and 4.64% based on this sample. Okay. Questions? This one you can't do in your calculator. It doesn't have a special one. Nope, you gotta do this one. I know. I don't think it does. Tests. No. Maybe. Actually, hold on. Let me check. All right. I'm going to do this by hand mostly, but in your calculator, stat tests, and then we're going to go down to, so keep going past this. This one right here, A. 1 proportion, Z interval. Okay, not the 2 proportion, just 1 proportion, Z interval. And then you need the raw data. So it's X is the number in the proportion. So that's the 54. N out of 1,500. And then our confidence level is 0.97. Calculate. There you go. Use it to check your work. Because I'm going to ask you the margin of error, and you can't get the margin of error off of this. Well, you could, but it would be more work than actually doing the problem. All right. Let's go to the next part. On the wrong page. Okay. So each autumn, the consulting firm PwC surveys 2,000 Americans regarding their holiday spending plans. This year, they found that 54% of respondents plan to do the majority of their holiday shopping online. So see, if you were doing this one, it didn't tell you how many, but you'd have to do 54% of 2,000 to get the X there. Okay. All right, so determine the point estimate. That's your 54%. Okay, so P would be 54 or 0.54. Let's go ahead and find Q. That should be 0.46. Okay, 54, 46 adds to 100. Our sample size, 2,000. All right, margin of error for a 90% confidence interval. Margin of error, this is a proportion, so we want Z times the standard deviation of P hat. Okay, so we'll go ahead and find the standard deviation of P hat. That's going to be the square root of 0.54 times 0.46 over 2,000. All right, so square root, parentheses, 0.54 times 0.46, close that, over 2,000. That'll give us 0.0111. All right, and what's the Z value that corresponds to 90%? That should be a common one. Getting close to getting that memorized. .645. So we're going to do 1.645 times 0.0111. And that'll be 18.2595. All right, so that is going to be, that's not, the decimals are off because I put 1645 and not 1.645. 1.645 times 0.0111 will be 0.018255. 0.018 and then 3. We'll round that. All right, so that's our margin of error. And then our confidence interval for 90% will be P hat plus or minus E. Okay, so our P hat, 0.54, plus or minus 0.0183. So 0.54 minus 0.0183 will give us 0.5217. And then 0.54 plus 0.0183, 0.55. Okay, so you're 90% confident that the true population proportion of Americans that shop online for holidays is between 52.17 and 55.83% based on this data. Now, if I'm doing this in my calculator, I would need the x, which is not given. The x would be the 54% of 2,000, so we would have to do this. 2,000 times 0.54. So 1080. And then it was A, go up this way. So 1 proportion z interval. Ooh. There we go. All right, so 1080, 2,000, and then 0.90 confidence interval. There you go. All right, next example. A political campaign would like to estimate the proportion of likely voters that plan to support their candidate. A campaign staffer selected a random sample of 30 likely voters and asked them if they plan to vote for the candidate. These responses are given below. All right, so we have the raw data. Yes, no, yes, no, yes, no. We got to figure out how many there is. So determine the point estimate for the proportion of yes. So how many yes do we have? 19? You guys get 19? 19 yeses. And then how many total? It says it. Don't count. 30. Okay, so in your calculator, the x would be 19. The n would be 30. Okay, but the p would be 19 divided by 30, which would be 0.63. That's your point estimate. All right, if your point estimate is 0.63, or your p is 0.63, your q should be 0.37. And remember, our sample size we got is 30. So the margin of error proportions, we're using z. So z times the standard deviation of p hat. So let's see, standard deviation of p hat. We're going to do 0.63 times 0.37 divided by 30. We want the square root of that. So square root, oh, there we go. Okay, 0.63 times 0.37, close parentheses, divided by 30. We're going to get 0.0881. All right, and a 96% confidence interval. If we look at, is that one on the chart? If it's not, we'll do 1 minus 0.96, which is 0.04, divide by 2, 0.02, and then we'll go inverse norm, 0.02, 0, and 1. 96%, yeah. 2.05, let's see. .05. Okay, you can go 4 decimal places out if you want in the calculator, but not really necessary here. All right, so margin of error, we're going to do 2.05 times 0.0881, which will give us 0.1806. So there's our margin of error. Then our confidence interval will be p hat plus or minus e. So 0.63 plus or minus 0.1806. 0.1806. So 0.63 minus 0.1806, 0.4494. And then 0.63 plus 0.1806, 0.8106. Okay, this has got a pretty big range. We had a really small sample size. And our P and our Q were pretty close together. Okay, so a lot of it is really same type calculations. You're just trying to determine if you're using T or Z first. That's going to be the hard part. Let's go ahead. One other thing we have is finding a sample size. Okay, so the sample size required to produce a confidence interval for the population proportion with a maximum margin of error. So now this is just in a proportion, what would be the required sample size if I want my margin of error to be 1%, 2%, 5%, etc. Z is going to be the desired level of confidence, and then P is going to be the sample proportion. Sometimes it's not going to tell you P, okay? If it doesn't tell you P, you're just going to use 0.5 for that one. So 0.5 for both of them. Okay, so if no P is given, so just write this on your thing here. If no P hat given, use P equals 0.5, Q equals 0.5. So for example, suppose the campaign staffer in example 3.5 knew about the above result before collecting any data for the confidence interval. Determine the most conservative estimate for sample size required for the 96% confidence interval. In the example, if we wanted a maximum margin of error, 2%. Okay, so in example 3.5, the P hat was 0.63 and Q hat was 0.37. Okay, so following this formula, we would do 0.63 times 0.37 times, what was our Z value for 96%? 2.05. Okay, so times 2.05 squared over the margin of error squared, which would be 0.02 for the 2% squared. Okay, so let's see. 0.63 times 0.37 times 2.05 squared gives us 0.9796. And then we're going to divide that by 0.02 squared. So 0.02 squared. 0.02 squared is 0.0004, just so you guys know. What's that? 2449.007. Okay, you gotta round up. A lot of you on your test, when we were doing this, didn't round up and you gave me the exact decimal. I did not take points off for that, but you need to round up. You can't have 0.007 of a person. You have to round up. Okay. Part B, Suppose the data collected in your example 3.5 serves as a preliminary estimate. Determine the sample size required for the 96% confidence interval if the maximum margin of error allowed is 2%. Okay, so it seems like it's the same question, but this is just saying I don't know what the people are going to say. So this is where we don't know P and Q. So here P and Q are unknown. Okay, this is preliminary. I don't know what they're going to say. I need to figure out how many people I got to survey here. I'm just going to estimate that P is 0.5 and Q is 0.5. Okay, and I want to do a 96% confidence interval. I need a maximum margin of error of 2%. So what we would do here is we would do 0.5 times 0.5 times our 2.05 squared divided by 0.02 squared. So we would go 0.5 times 0.5 times 2.05 squared. And then we would divide that by 0.02 squared. Oops. Divided by 0.02 squared. There we go. 2626.56. We got to round that up. So I need at least 2,627 people if I don't know what they're going to say. As we found earlier in the chapter, the best way to decrease the margin of error and thus shrink the overall width of the confidence interval is to increase the sample size. Okay, although decreasing the level of confidence will also shrink the margin of error, this is not advisable since confidence levels are set by discipline. Remember we talked about the medical level of confidence, and it should always be adhered to. Right.